So many questions. Okay. Now, as you can see in the first page, there are the logo of 3 European projects which I lead. And recently, I started putting Iran universities in this project because European Union is encouraging us to put outside the Europe university as from Pakistan, India, and Iran. And so if you are interested in what I'm doing, please contact me and we try to establish more ties, because it is very important to me that the lead people, the lead theory people get together. Here is a quick plan of the talk. I am not sure I will be able to cover in detail everything, but I will explain what real forms of Lie algebras are and what is the Cartan decomposition. For me, the ordinary setting, so when I write like here, wait, when I write like here ordinary setting, I mean the non-super one. So I use to annotate the file so you see. And then after I introduced these concepts, I will define admissible positive systems. The first one to consider them was Chandra in his famous papers on the representations of real semi-simple groups. Then we extend the same concept for real forms and Cartan decomposition for Lie superalgebras and the concept of admissible system, which is the same. These systems are fundamental to construct representations, infinite dimensional representation of real groups. And this was done by Chandra, and with Professor Varadarajan and other collaborators, we extended this beautiful theory of Harishchandra to supergroups. So we constructed this representation. We are not going to talk about this today. This is deserves a talk on its own. Today we limit ourselves to the Lie theory part of this beautiful representation theory question. This is a joint work with my co-author, Professor Meng Kiat Chua at the University of Taiwan, and Professor Ivan Dimitrov at the University of Queens in Ontario, Canada. And I know that you already gave a talk about some work we did together, but not regarding this special topic. So let me go down. Sorry, I'm a bit... okay. So let us talk about a real form of simple complex Lie algebras. So we know all that there is a one-to-one correspondence between real forms and antilinear involutions. This is kind of obvious, right? Because I didn't write it here because, so sorry, just I didn't write it here, but real form correspond at sigma from G to G, which is antilinear, meaning that it sends a complex number to its complex conjugate. And in fact, you get the real form as the fixed points of this involution. However, if you complexify the antilinear involution, you get a linear involution, and this involution is called theta. Okay, so it is important for me to convince you that real forms correspond to an antilinear involution of the of the complex Lie algebra, but then if you complexify, you get a linear involution. For example, let us look at a very trivial example. This is SL2C. These are the traceless matrices, complex. What is the Cartan involution? This is a very special one, since all the elements of the Cartan, so this is the element 1 minus 1, to minus itself, and then sends a root space to minus x to the minus alpha. So a root space is in this case 0, 1, 0, 0, it is sent to -1, 0, 0, 0. Now, this is an antilinear involution and it corresponds to sending a matrix to minus its complex conjugate transpose. You can verify this by exercise. In this case, theta is the identity. So it's a degenerate situation, and the fixed points are what is called the compact form, because SU2 is evidently not compact because it's a vector space, but the group corresponding to this algebra, the simply connected group, is SU2, and this is the Lie algebra of a compact group. And for this reason, is called compact. Now, a less obvious example is theta, that is linear, and it is the identity on the diagonal matrices, and sends x alpha to minus x alpha. So this will send the element 0, 1, 0, 0, 0, -1, 0, 0. And this, some calculation are required, but they are all very simple calculation. Will tell you that the fixed point are SU11, which is isomorphic to the real form SL2R. So far, so good. Ashgar, do you have a question? Please, guys, ask me a question. There is no problem. Everything you see, you understand. Ashgar, am I still
Yeah, that's
showing?
good. Yeah.
Perfect,
I
perfect. I
will
just
check your
want
chat. Yeah. I will check the
please
chat box. If
check.
there is any question, yeah, I
Thank
will
you.
ask you. Don't worry
Thank you
about
so
that.
much.
Yeah. You're welcome.
No, I worried that you don't see, and I'm speaking to
Hmm.
nobody. That is the problem. Okay,
Okay.
that is very good. So in this correspondence that we just discussed, real forms of a Lie algebra and involution, and I insist that these are involution, meaning that these involutions are linear and theta square is 1, that is the meaning of involution, correspond to something called Vaughan diagram. I will explain what it is, okay? But at this point, I think it is important to consider, to remark that theta is the complexification of something called Cartan involution, the real one, that will allow to split the real into its compact, maximal compact subalgebra. This is this KR, this object, and the PR, which is a KR module. What do I mean? So KR, it has the property that is a subalgebra. So KR bracket KR is inside KR. But PR is a module. So KR bracket PR is inside PR. Finally, we have this last property. Take notice of this property because it will come again. When we complexify theta r, we get the complex Cartan decomposition. I speak about K as compact. This is very wrong because, but it's the normal way to speak about it. K is a complex object, so it's not real, and so it is not compact in any way. This is, in this decomposition, remember that theta square is equal to 1, so +1 and -1 are its eigenvalues, and we can decompose G into the +1, which is K, P -1 eigenvalues of theta. And this bracket simply tells me that if you bracket two elements that have eigenvalue -1, you get an element of eigenvalue 1 because theta is an involution. So it's a very straightforward calculation. I also wanted to give a very explicit example. This is the same example as we did before. This corresponds to SL2 R So the real decomposition is SO2R, so the rotations in R2 plus these matrices P, which are symmetric, okay? And one can see straightforward that this is the composition. If you have some patience, you also verify everything that is written above, okay? So it is all the things I written, they're really a very simple calculation for SL2C. Okay, so far so good. We know there is a real form of a complex algebra, but especially what I think must be very important is this yellow thing, that real form corresponds to complex involution. Now, depending or not on the fact that you may or may not have seen the theory before today, the real Cartan decomposition is unique up to conjugation, of course, up to isomorphism. So if you are looking at real involution, sorry, if you're looking at decomposing, so perhaps, so if GR decomposes as KR plus PR, this is unique with all the properties described above. So these properties right here, these yellow properties. But if you try to do the same decomposition, G as K plus P, this decomposition is not unique. We have as many decomposition as theta, or if you prefer, real forms. So these are many, okay? So the same thing is like this one is unique for SL2R. And this guy here is not unique. No, there is another one. The one where you have just SU2 plus 0. Okay, so I'm just warning that Maddie, you have a question? Hello? Please feel free to stop me, ask me questions about that. No questions. Okay. Ashkar, can you check if there are questions? Because it seemed to me perhaps somebody wanted to ask.
I checked that.
Okay.
There is no
Thank
question,
you.
yeah. At this moment, yeah.
Hello? No. Okay, but feel absolutely free. Okay, so real forms are associated to Cartan decomposition, are associated to involution of the complex algebra. Now I'm asking a further, so I'm putting a further hypothesis that G and K share a common Cartan subalgebra. So they have a maximal abelian semi-simple algebra they share. Okay, this is really an extra condition because this fact is not granted, but we can assume it. I mean, the theory assumes it. Fine. In the example that I just described, it is the case, but it's a very simple example. So in many cases, this is not satisfied. Okay, so here I wanted to give, to extend this example. Perhaps I do it very quickly. So we have, if we take SLMC, so these are the traceless matrices which have, I divide into blocks. Okay, so this is M, N, M, N. And I can write explicitly I can write explicitly an involution, and this involution will split into what I call the K, the complexification of a compact algebra. So this will be K plus of diagonal block matrices, which are the P. And if you do the silly calculation, you verify that K is a subalgebra. This is really very quick. I mean, it is clear, but most interesting that P is a K module. So you can do this little calculation. It is, I mean, practically straightforward. And this K is, so this K is what is called SUM. Sorry, you can see it is SUM, SUN plus IR. It will have a center. So this is a center. The fact that I say there is a center is not just a curiosity. This center plays a key role, okay? Let me give an overview because the real form that we're, so if this is G, the real form corresponding to this object is what is called GR SUM, N. This is the real form that will have a, oh, I'm sorry, here is complex SL, and then there'll be C. I apologize. So this will be some KR, which will be SUM plus SUN plus IR plus PR. Why am I saying that this center in K plays a key role? Because one can show that GR mod KR, that's clearly a real vector space, but this vector space has an invariant, a GR invariant, complex structure. And this complex structure is integrable. So it will go to the space GR, and this is a key in the Harish-Chandra representation theory as a complex structure. Okay, I will not go further, but this center is given the complex structure. Okay. So no questions, Ashkar. Can you check, please?
So far, there is no question, but dear Hiroshi, try to correct your typo, actually. The SU, you mentioned about that.
Oh, yeah.
Yeah.
I made a mistake. It was SL.
Yeah,
I apologize.
it was a typo.
Okay.
Yeah, it's not
Sure.
wrong. Yeah.
Thank you. Okay. Now, very, very quickly, because of course, I mean, not of course, but many of you will know that simple complex Lie algebras are classified by Dinkin diagrams, where we essentially have to pick a positive system for the root system, and in the diagram, every node is a simple root. It is impossible for me at the moment to explain fully this theory, but essentially you can define this epsilon I, which I will come back, from diagonal matrices, for example, A1, that so AI will give you AI. So the diagonal matrices are your Cartan subalgebra, and roots for the A-type are, so the A-type are given by alpha I, epsilon I minus epsilon I plus 1. And we establish a link whenever a scalar product, which is really the Euclidean scalar product, think of it as vectors, is different from 0. This is an extremely quick way to explain it, just a reminder for everyone that already knows. Now, this root system will have a lowest root in the sense that there is an order coming from the definition of what is a positive root, and extended diagrams will have also the in green So this green dot represents the lowest root. Now it is interesting because while for the ordinary setting, no problem, you can define real forms, you can ignore these extended linking diagrams. As we will see in a moment, if you look at real forms of superalgebras, it is very interesting and important to look at the extended. But we'll see in a moment. Okay, so what is a Vaughan diagram? I'm aware that it is most, what can I say? It is most known what are called, sorry, my cursor is not, what are known as Satake diagrams. Vaughan diagrams are an alternative to Satake diagrams, and actually to me it's kind of the opposite because in a Vaughan, if you know what it is, fine. If you don't worry about that. In the Vaughan, you select the maximally compact real. In Satake, you choose the opposite choice. So somehow are opposite diagrams, but of course it doesn't matter. It's a matter of preference. They both classify the real forms. Okay, so let us see how a diagram, Vaughan diagram, is associated to a real form. The rule is very simple because if we do this decomposition, because of the condition on the equal rank, meaning that the Cartan subalgebra sits inside the compact K, we can write the compact as Cartan plus sum of alpha, and we call this alpha compact, while P will be written as a sum of other G beta. We call this beta non-compact. Perfect. Now, what we can do, we can assign, for alpha compact, when we have the diagram, so the rule is the following: we paint or circle, depends on the convention. Okay, I put paint and circle because we circle, but other people paint, so it doesn't matter. You mark in some way a, a diagram whenever you choose your root to be non-compact. So, for example, look at the case of SL3C. So the root space, sorry, the root system is alpha, beta, alpha plus beta, plus or minus. You can represent this in two-dimensional vector space. I will have this picture also. So this is alpha, beta, alpha plus beta, and then the minus, of course, and so on, but you don't care because these are determined. Okay, so in this, we have that this alpha is non-compact because theta sends it to -1. So this is a -1 eigenvalue. You remember that P is the -1 a value, while K is +1 a value. Great. And so we circle this root or we paint it, while beta is not painted. Now, when you take a vector that is, this is something kind of stupid, right? If you take a bracket of a -1 eigenvalue vector with a +1, you get a -1. So if you do like x alpha, x beta, so this, if you do theta, this will be sent to minus x alpha, x beta, because that's an involution. So this alpha plus beta will also be painted, okay? So if you represent your, you take the diagram of SL3, then you paint alpha because, or you circle it. So alternative, is the same, alpha and beta. Now, I also wanted to point out, but perhaps I'll do later, that we have a choice of systems, right? So you may say, wait a moment, there is also another diagram corresponding to it, which is the following, where you paint both. So this will be like, if you choose the, okay, so if you choose this is okay, what do I want to say? No, I don't want to say it now. I don't want to say anything now. Let me go to the classification. So what you can prove is that you can classify real forms by these Vaughan diagrams. So essentially, these Vaughan diagrams are telling you theta, and by telling you theta, they're telling you the real form. So for example, for this SUPQ right here, theta, the linear involution will be that you have like alpha 1, blah, 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 till you reach some alpha r. So H goes to itself, and then you have X alpha 1, alpha I goes to X alpha I, and then you reach this X alpha R will go to minus X alpha R. And then you basically have your simple roots that generate your Lie algebra. And by specifying this diagram, you are giving me the theta. This is the celebrated Borel-de theorem that will hand you, given a diagram, a theta, and vice versa. Notice that I am cheating now because I assume in my considerations that H is inside of K is inside of G. If not, it is more complicated, okay? Can be done, but more complicated. There is perhaps a question. Ashgar, can you check it, please?
No, there is no question.
Okay.
Yeah, I checked.
Okay, but so far so good. Okay.
Yes, of course.
Okay, very good. So we forget about the more complicated cases. We focus on the equal rank one. Okay, perfect. Okay, finally we arrive to the meat of the talk, which is what it means for a rooted system to be admissible. Okay, so we are still in the equal rank hypothesis, this hypothesis here. Sorry, I'm sorry. I don't know why it does it. Okay, whatever. We are in this hypothesis that there is a Cartan subalgebra inside the compact. We have a complex Cartan decomposition where the K is the fixed point, so the eigenvector of eigenvalue 1 of theta, and we have the decomposition I spoke before. But right now, we fix a positive system. If we fix a positive system, we can put all the positive root of P on one side. So we can put them aside. So this BG alpha positive, and then the negative here. Great. And then this is, we say that the system is admissible if it has these properties. We know that K fixes P, but we want something more. We don't want just to fix P. We want to fix both the positive and the negative part. Moreover, we want a very strong property. We want the property that P plus P plus is equal to 0, and same thing of P minus. If you are familiar with Lie algebras, you know that this is very peculiar to have this subalgebra. Now, in the theory of groups, Lie groups, this corresponds to an abelian group. So this is the celebrated Harish-Chandra big cell, Harish-Chandra decomposition that allows to create a very big open cell inside the complex group. I give here as an example the case of SL2C, where I give explicitly K. Now K in this case, K is equal to H, so the compact is coinciding with the Cartan, and they are diagonal traceless matrices. P plus and P minus are exactly the span of positive and negative root. Okay. Okay, so I wanted to show to you that if we have an admissible system for a Lie algebra, it's not that all positive systems are admissible. Let's try to understand this very well. So if we take, for example, so here we decided to take as our, so I change the, so we take this as the painted root and this as the non-painted one. So this, sorry, this is alpha and this is beta. Alpha is compact, beta is non-compact. So this is also non-compact, this is also non-compact. Now, if we pick this alpha and beta as a simple system, we have the beautiful situation that if you take, sorry, so if you take x alpha, x beta, this is inside C alpha plus beta, which is non-compact. Perfect. If you do x minus alpha, x beta, this is 0, so perfect also, because you want k, p plus to be inside p plus. Okay, even if you bracket by compact negative root space, that key point. In fact, Harishchandra calls these roots totally positive. So x beta for Harishchandra is not just a root space of a positive root, it's root space of a totally positive root, because even if you bracket with a negative root, you stay positive. Now, if we look to this positive system, the one determined by this hyperplane, so minus beta alpha and, sorry, minus beta alpha plus beta and alpha, this is not admissible. Why? Because if you bracket this x alpha, x minus alpha, x alpha, wait a moment, if you bracket, yes, if you bracket, sorry, is failing the condition p plus equals 0, because if you take x alpha plus beta, x minus beta, this is x alpha, so it is non-zero. So this is not admissible, because admissible means that you decompose G as K plus P plus P minus, and these are abelian. But here, no. What happens is that this bracket is non-zero. Okay. So these positive systems are a bit delicate, because even if they exist, it's not that you pick one and it is admissible, not necessarily.
Sorry, can I have a question?
Sure, please.
Uh, is it possible to define an admissible basis? I mean base, a set of simple roots that give us a positive system admissible?
That is very smart. It is very smart to ask, because indeed the property of being admissible is inside the simple. Okay.
Oh.
These are yes, these are very special systems where the number of non-compact roots is minimal and equal to 1. Okay. Because in this case, you see that the base had the two non-compact, right? The base is this here, right? And
Yeah.
whenever you have this situation, you are in trouble, because you bracket them, you get the the K and you're done. But yes, they can be characterized in terms of simple. Yes. What are the simple system?
Mm-hmm.
And more precisely, I didn't want to say this because Ashgar, you want something technical, but I will say, since you mentioned, no, but it's very good. It's very good because this is due to constant. This is work with Dimitrov. This admissibility is characterized by saying that the simple system of G consists of a simple system of K completed. You see?
Okay, thank you.
So if you get a simple system of G, sorry, why did I write? So if you call pi the simple system, this is the simple system of K union something else. Okay, whenever you have this, then it is admissible. Even Arishchandra comments on this, but this is, I know it looks very simple as I say it, but it's very complicated. I will see the theorem right now, and I will say some words. Okay, so if you take an
Thank you.
involution, yeah, but I'm happy to answer. Really ask me anything. So suppose you have an involution, it is equal rank, as we say, if both K, the fixed points, and G share a common Cartan subalgebra.
Sorry, Rita.
Yes,
We have a question in
yes,
chat box. What do you mean by
please.
equal rank? Someone
Yes,
asked.
I was, no, but it's very good. In fact, in this slide, I recall, because of course, how can you remember something I said at the beginning? So equal rank means that you have a Cartan subalgebra H, which is inside of K and G. The same Cartan both for K and for G. This is not obvious because K is a subalgebra, so in principle you may have a Cartan which is smaller in rank, obviously, I mean it's smaller algebra, and in fact it may happen, but we assume to be in this hypothesis. Did I answer? Perhaps. Yes?
I'm waiting
I
to
don't know who
the
asked, but did
response.
I answer the question? Aha, okay, very good.
Yeah. It seems to me that is okay.
Okay, 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 thank you. Okay, we say that theta is admissible if we have an admissible positive system with respect to the decomposition in plus or minus eigenvalues, because theta will give you this complex Cartan decomposition, and we say that theta is admissible if there is a positive system for which we can do this decomposition, satisfying the property which we mentioned above. So the property is this, that we just quickly, and abelian. As I said, not all the positive system will do it, but we call theta admissible if there is at least one. Then we say that theta is Hermitian if the quotient of GR mod KR, the real, has a G invariant complex structure. Now, Arishchandra proves that all simple complex Lie algebras which have an Hermitian theta have an admissible positive system. And it is beautiful because Arishchandra gives also the complex structure. And this complex structure intertwines P plus and P minus using the center of K. Now, if you read Arishchandra, is beautiful and very conceptual and complicated. However, if you go in the books, like for example of Knapp, or the book by Helgason on the same topic, what they do is something very different than what Arishchandra does, because you have the Lie algebras, there is classification. So what they do, they go through case by case, A, B, C, D, and the exceptional, and they verify the existence of an admissible system. Of course, I think that both Knapp and Helgason are great mathematicians, but none of them is the great Harishchandra. So Harishchandra wanted a treatment that was independent from the type. They only check case by case that there exists, but Harishchandra gives a full proof. And I personally consider this a beautiful theorem, but okay. Now that we have reviewed the regular case, we may ask, is this true for a contragredient superalgebra? Can you do it for affine? Can you characterize through Dinkin diagrams as Vaughan? Can you generalize? And the answer is yes, you can do this, and this is my work. And I know time is running short, so I will illustrate my work without, of course, details. The only thing that we have not done yet is the super case in full generality. We did some work, but not in full generality. So yes, so the purpose of my research on this topic was to extend this beautiful theorem of Harishchandra in a conceptual way to this more general setting. Because if you check a case by case, of course, is a stupid thing. You just check that this system exists. Okay. Now, very quickly, what is a Lie? Because I want to give time for answer. What is a Lie superalgebra? It is simply a Z2-graded vector space. We call it super, that has like a even part and an odd part, but instead of, when you have a bracket, instead of having anti-symmetry the usual way, there is a minus sign coming from the parity of the elements. And same thing for the Jacobi. The key example to keep in mind is the Lie superalgebra of supermatrices. Indeed, it is a vector space. I specify what the even and the odd matrices are. And key point of this slide is this bracket. This is super bracket that takes the place of the usual bracket among the matrices, which is this. This holds for the even elements. For the odd elements, you write a plus sign. Simple like that. This is, I think, very quick. Okay. Contragredient superalgebras were classified by a famous work by Katz, and are really more difficult to classify because, for example, Dinkin diagram depends on the chosen simple system. So you may have different Dinkin diagram associated with the same algebra. And I put down the simple contragredient. There are families and there are exceptional. Is not super crucial for this talk that we discuss them. I think that the most important one is the type A, which are the super trace zero matrices. Notice that for the trace, but this you already know, you put a plus. For the super trace, you put a minus. Now, what is the consequence of this fact? This is not just an example, it's a reflection on a more deep concept that the trace in the Lie theory defines the Cartan killing form, which is a positive definite product on the Cartan subalgebra, also on the real part, whatever. And this is a crucial product because the root systems live in this real space and so on. Now, the super trace define an invariant scalar product, which is not positive definite. It is non-degenerate, but not positive definite. This opens a lot of problems for me, opportunities to understand what happens and in a more deep way. And this is actually done by work by me and Dimitrov, reasoning on constant root systems with this lens of this product. Okay, there is an observation by Chua in 2012 regarding what are called distinguished extended Dinkin diagram. We already spoke what are extended diagrams. We add to a Dinkin diagram the lowest root. You can do the same also in the supersetting. Something very interesting occurs though, because in the supersetting, you can show that there is a unique extended diagram which has a very interesting property. If you remove the odd roots, you see this, you obtain the Dinkin diagram of G0, the even part. This is for me very interesting. The semi-simple, because of course the even part may have center. Then if you look at the odd roots that I call D1, then the number of odd roots -1 is the center. And you discover that some Lie superalgebra, the even part has no center. Sorry, not the even part. The even part has no center. As we say, center is crucial to obtain the complex structure that in the ordinary case is linked with the existence of admissible system. You remember that there are three things that are the same: existence of Hermitian theta, that is complex structure on the quotient, the existence of admissible system, and a certain properties on the algebra. Okay. These are the extended. I don't have the time to explain in detail the MN case. Okay, in the super case, we have, due to Chua and other people, Parker, Katz, there's a lot of people classifying the real forms. I forget to put down the credits. So it is Katz first, and then there is Parker, and then there is Chua, and many others which I certainly have forgotten. They establish a superalgebra correspondence between the real forms, but notice the fantastic appearance of, and me myself. Why did I forget me? Of course, I also participated. Notice that instead of playing involution, I am sorry, it is 2-4, I apologize. So these are involution on the even part, but they have order 4 on the odd part. So when restricted to the odd part, it has order 4. Now, this is very interesting because you may say, oh, what if you look at the involution? If you look at the involutions, there is no meaningful real form associated with it. And then the next step that you want to do is to look at Vaughan diagrams. They classify super real forms of superalgebra. So let me go. I wanted, but I'm running out of time, so I don't have the time. So Chua in 2013 used extended Dinkin diagrams, the so distinguished one, to classify the real forms. Exactly, so the result is absolutely analogous to the one for Lie algebras. He employs the distinguished Dinkin diagrams and paints them. Instead of painting, he circles. So the dot is now replaced by the circle Y, because the dot in super word means that we have an odd root which is non-isotropic, while the cross is isotropic one. But okay, it doesn't matter. Important. Well, it is very important, but I don't have the time. Okay, so this is the full classification. Sorry if I go a little fast. Perfect. So let us go to the contribution that I gave together with Chua starting from 2015 up to 2022, because it's a series of papers. We define equal rank for super algebras, quindi G, so G is a complex contragredient superalgebra. And then I define what is equal rank, same thing. You want K and G to share the same Cartan subalgebra. Notice that this notion was, see, this one is replacing P plus equals 0. Why is it so? Very simple, because P will have even part and an odd part. Now, the even part is eigenvalue is -1, theta eigenvalue. But the odd part will have eigenvalue plus or minus I. So what happens if you bracket two elements that have, so if you bracket two vectors that have eigenvalue I, you realize that you get an eigenvalue -1. So this will have -1 eigenvalue. So you cannot land in K, or you cannot be 0, but it will be -1. So you have to relax the condition, otherwise you get nothing. Because remember that theta 4 is equal to 1, so the eigenvalues are ±1 plus minus I. I forgot to indicate Gavarini as one of my co-authors that worked on this. Shame on me. Okay. So I put down the result with Chua. So if we have a complex called a gradient superalgebra, we are in equal rank condition. If its even part has an admissible positive system, also G has an admissible positive system. So the admissibility on a positive system extends for G0, extends to the whole superalgebra. We applied together with Varadarajan this result to construct a super Harish-Chandra representation of infinite dimensional Lie supergroups. Not for today, of course. With Chua, we classify the real forms that correspond, but we also prove in the theorem of Harish-Chandra, sorry, here is all the diagrams, this result that in the case of theta admissible, then the quotient has an invariant complex structure. So we prove that theta Hermitian is equal to theta admissible, which is exactly what we had the theorem of Harish-Chandra. I wanted to finish 5 minutes before. Let me just give a quick, brief overlook that with Chua, we also examined, as I said, a situation where instead of getting a involution, we look at a finer order automorphism, and we establish a correspondence between Levi subalgebras and what we call admissible automorphism for Lie algebras, not superalgebras. So there is still work to do. Of course, I mean, we try, we go back to this. Sometimes we don't do just this in our lives, so it's a lot of fun, but okay. So I guess that all the things I wanted to say something more, but I'm running out of time. I think I'll be very happy. Thank you to finish here. Thank you very much.
Thank you so much. I really enjoy. Sorry. We will go ahead by questions and comments. Please welcome.
Yes, please.
Rita, can I ask a question?
Absolutely, yes, yes.
Yeah, for like Lie algebras, like toroidal Lie algebras, so there is not a notion of positive root systems or something like that. Is there any kind of result for this kind of Lie algebras, like toroidal Lie algebra?
I don't know, Toroidal. I'm so sorry. You caught me. I don't know. See, I'm a bad student. I don't know this theory. Who is
Okay, no, I mean,
speaking?
like
Can I?
like
Professor
tensors.
Azam, Said Azam is speaking. No.
Hazza.
Yeah.
Okay, very
Yeah.
good. Yes.
I like if you consider a finite dimensional simple Lie algebra,
Yes.
and then tensor product it with complex with Laurent polynomials in two variables.
Yes, of course we have that. Yes, we proved it. It's here. It's in, yes, I show. Is yes, we look at that. Yeah. Wait. Yes, you are very correct. Wait, because, wait. I have to go to the first slide because I put down my work with my collaborators, and now I understand what you mean. Right. So these are appearing in the Kac-Moody. Am I right? This is what you're saying, the loop algebras, right? Is it what you refer to?
Not really, because this is like affine or untwisted Kac-Moody Lie algebras. It just what you consider in this case, it's just you tensor product with Laurent polynomials in one variable. But I'm asking if
Yes, but yeah, but this will be part. So if you look at the Kac-Moody algebra, it will
okay.
be like a subalgebra of that, right? No, but I
Okay.
see what you mean. Yes.
Okay.
No, we looked at the Kac-Moody, but we didn't look at the toroidal. You are right. We didn't.
Right.
Yeah.
Yeah, because
Yes.
in that case, you don't have any notion of positive systems if you consider toroidal Lie algebras in general. And it would be a problem for you, I guess, because there is no notion of positive root system in that case.
Yeah. Yeah, perhaps. Yes, I don't know. We didn't look at them because we were motivated by the theory of representations,
Right.
and toroidal are not so hot in representation theory. Am I right?
Well, they are also important, but well, maybe you are, some other people are interested in this kind of algebras. Okay, thank you.
No, okay, but thank you.
Thank you.
Welcome. I hear something. No.
Questions. Okay.
Yeah.
So can you please
Others?
share with me also the recording, because one of my
Yeah,
students
of course.
wanted to attend but could not. So he
Oh.
will be very happy to see the recording.
Of course, I will share it with you. I have some question
Perhaps,
actually.
okay.
This is my question is general case. Yeah. What specific complications does the super case?
Yes. So the super case is complicated, as I said, by the fact that the classification is, dinky diagrams do not classify, but we bypassed it with the distinguished one. And then by the fact that you need to look at this modified property. That is the thing. But then you are right. Once you understand, you try to push through the proof, it will go. So in some sense, you are correct. You don't have to invent a new approach. You have just to invent a new definition, because the usual one will not work. But once you modify, instead of involution, you take this or different order, and you do all the right. Once you put all the puzzle together, then it will go straight. You are right. It's not like we discovered a new proof. So the difficulty is the definitions. Yeah.
Thank you. And I have a question, another question.
Okay.
Could you state the precise condition that means a positive system admissible? Is it related to the existence of a particular Borel subalgebra?
So wait a moment. This is a question for super or no super?
Both. You can consider both. About non-super?
Oh, okay, sure. I mean, positivity. Okay, let's talk about the algebras first. So positivity is equivalent of a chess of a Borel, right?
Oh.
So yeah, I mean, a positive is a Borel, right?
Mhm.
So you may say Borel, yeah, it's like an admissible Borel. Yes,
Mhm.
that's if I understand correctly. And with the super, the thing is more complicated because you also have the extra difficulty that not all, so the Weil group doesn't have enough symmetries, right?
Mhm.
So in some sense, we are cheating in the sense that we're not telling you what are all the admissible systems, but we're saying, give me an even admissible system, we construct out of it the whole thing. So we're like taking simple systems that have just one odd root. Okay,
Mhm.
so that's the way we do it. So we're taking very special Borel. We're not taking all of them.
All
My
of them.
impression, it'd be a good question to see, are there other admissible? I would think not, but we didn't formulate our question in that way.
Mhm.
Okay.
Thank you. Please welcome if you had any question.
Yeah, I have another question.
Please
Very
welcome,
happy.
Said.
I'm very happy. Yes.
So Rita, you have a paper with admissible positive systems of affine non-twisted Kazmodeli
I do.
algebra.
I
Yeah.
do. Yes.
What happens for twisted case?
Oh, I do have that too. I have another paper. I didn't put it there because I found it boring to put all my papers there. So
Okay, okay.
yeah, we do it for also twisted, indeed. But the
Okay,
thing we're not doing is the super affine that we are doing right now. We're working on it as we speak. We want to
right,
do it.
right.
Yeah,
Okay, thank you.
Mm.
yeah.
Actually, you are going to work about super affine?
I want to. Yes.
You want to or already done?
No, we are doing it with the
Uh-huh.
Chua. Yes, and I
Okay.
was so happy to give a talk because this gave me the focus on what I'm doing with him now. So it's
Mhm. For both cases, I mean twisted and untwisted, super affine?
give us a break. Let us go slow. We say what we do, right?
Okay. Thank you.
Okay. More perhaps somebody else was asking. I don't know. The chat. I don't see.
I will check. Yeah. No question.
Okay.
Just I can see. Thank you for your interesting talk.
Okay.
Yeah.
Thank you
Okay.
for inviting. It was a great pleasure. Okay.
It was my great pleasure. Yeah. Okay. Uh, on
Okay.
behalf of everyone here, thank you, dear Rita, for the excellent and great
Ah,
presentations. We
too
deeply
nice.
appreciated your insights. Yeah. Thank you
Very
to
good.
all. Thank you to,
Okay.
yeah. This
Bye
concludes our
bye.
webinars. Bye. Goodbye. Have a good
Bye
day.
bye. Take care. Bye.